So the prevailing theory of the Big Bang is that out of the Big Bang doesn't arise just a single universe, but many, many, many universes. And people call this a multiverse. The usual picture of the multiverse is that globally it's like a fractal, like a mosaic of different little pocket universes, and each pocket is different from another pocket. The problem with the multiverse is that it doesn't really predict very much about our own universe. In a multiverse, everything is possible somewhere. Therefore, a theory of the multiverse doesn't say very much about what we should observe in our own local observable patch. Our new theory fixes this by essentially reducing the vast multiverse to a much more manageable, smaller, smoother universe. Our new theory is based on a technique which we have borrowed from string theory. And that seems to imply a much more manageable global structure of the universe, in which regions can differ from each other, but not at all as much as in the old theory of the multiverse. I think the key point about our model is not so much that constant density surfaces in the universe are finite, but rather that the variation in the multiverse is restricted. In other words, that the range of different pocket universes is much smaller. That makes the cosmology based on our new theory a lot more predictive, a lot more stronger as a scientific theory. And therefore, ultimately, we hope testable. Now, it remains very subtle to test a multiverse theory or to test any global theory of the universe, because there will always be regions or patches or histories of the universe in which we can't be. So any falsification of a multiverse theory or a global cosmology must take account of the fact that we are inside the universe. We're part of its history. We're not just somehow outside the system and looking at it. No, we're part of reality. This is very different from other scientific disciplines. It's a very subtle point with a lot of debate about it. And it's extremely difficult to implement if the multiverse is truly infinite. In our more manageable structure, which we propose, this comes taking into account our observational view, our viewpoint as observers within the universe will be much easier to implement. The early founding fathers of cosmology had a philosophical preference for a finite universe. They didn't have a concrete model of the Big Bang, of course, because quantum gravity hadn't been invented. But their philosophy is in line, I believe, with the model we propose. We are much more than you might think guided by our own local observations of the cosmos, our observations of our local patch of our universe. Those observations which allow us to reconstruct our cosmological history almost all the way to the Big Bang, those observations allow us to constrain our theories. And they're very much a guiding principle. Ultimately, of course, we will be interested in using our new theory not just to say something about the global structure of the universe, which is the topic of this paper, but also something about our local universe. The most promising observable when it comes to our local universe are probably gravitational waves. Gravitational waves not from the coalescence of black holes, but gravitational waves that are probably generated at the Big Bang, basically. The creation of space and time goes together with the generation of gravitational waves in our theory, and perhaps the detailed pattern of those gravitational waves will give us a key signature of our model. Those gravitational waves are out of reach for the LIGO experiment because those gravitational waves have a very low frequency. But the main European experiment to measure gravitational wave, the LISA observatory, which will be a space-based gravitational wave observatory, that should be ideally suited to capture those gravitational waves from the Big Bang. Every cool paper goes together with the Eureka moment, right? But unfortunately, for this paper, it happened quite a while ago. I think it happened roughly 3 years ago in Cambridge, when I was working with Stephen on sort of the first explorations of our new viewpoint of cosmology. And we stumbled upon this observation that it drastically changed the global picture of our universe. But we waited with publishing this because we first wanted some more evidence to support this conjecture. I applied for an ERC because at the time, 2-3 years ago, I had a rough idea of this new kind of cosmology. But there was a lot to work out. There was a lot to explore, and I didn't know where I would end up. So this seemed to me like the ideal context for an ERC project. I had a clear idea what I wanted to do, and I did not know where I would end up. While pursuing the ERC projects, the gravitational wave discovery came along. But those gravitational waves, as we discussed, will ultimately be the prime observable that I'm aiming for. So everything is nicely coming together on that front as well. This is fundamental science. I cannot predict what eventually comes out of a cosmology, but everyone is interested in the universe. So that seems to me good enough reason to pursue it.